Okay, I guess we can start. I don't know if any of you had a specific question first. How's everyone doing? No, I mean there might be questions from the earlier stuff. It's just like a lot of the earlier stuff. Anyways, you have to use it. The thing is like the only thing that this course you ever uses is like more or less reducing the matrix. It's just reducing matrices kind of take new forms depending on the problem, but yeah, like for example, like the topic of the determinant was on the second midterm, but like without it you cannot compute the eigenvalues or eigenvectors. But yeah, like it can still be um you should still check the older midterms and the older problems, but like the majority of the problems will be kind of new, if that makes sense. But yeah, you can still see um older problems and things like that. Yeah. Um, Anyone else? Or maybe well, to just to give you some time to think, if you want to ask me anything specific, just to clarify something, because it may not have been super clear. I mean, it was implicit in everything I did when we found the Gram-Schmidt basis. So if you remember, like the Gram-Schmidt method, uh, I mean, usually, like first, I mean, the eigenvectors can be different, like in the sense, like for example, maybe I should write this here before like saying what I wanted to say about Gram-Schmidt. For example, if like if v equals 2, 3 is an eigenvector, right? Um, then any multiple, which is any non-zero multiple of these, would be an eigenvector. So let's say divide by 2, like 3 halves. Sorry, 3 halves is an eigenvector. Also an eigenvector, and basically, and more or less any non-zero multiple, right? Actually, any non-zero multiple. So, in particular, that does mean it is because to find eigenvectors, finding eigenvectors is like finding a null space. Um, so there are different ways sometimes where you can write the answer. So if someone writes the eigenvector this way versus someone writing it this way, they're still correct answers because they kind of represent the same. I mean, like the important thing is kind of like the direction that the eigenvector singles out. So that will not change. It's just that that will be the same regardless of what anyone finds. Um, so, but yeah, like usually, like the matrix is uh, for eigenvectors, eigenvalues, especially because all the matrices we're working with are like very small, like 2 by 2 or 3 by 3. Like there is not much of a difference in how you could write the answer, but if the matrices were higher, like yeah, they could look a little bit. There could be more options. If that makes sense. So it's like the ambiguity in finding eigenvectors is not that different in the ambiguity than when, like, you know, when you find sometimes like a basis for a vector space or things like that. I mean, there are multiple answers, but usually, you know, for the examples we're doing, like they're all so simple, like they're those different answers are kind of easy to relate to one another. So if you found it correctly, you don't have to worry if the answer doesn't agree kind of with the like answer, for example, that I would write, because, like, you know, there are different approaches you could take, and things like that. Is that making sense? But yeah, so that's like a thing that sometimes is like a source of concern in this linear algebra, that kind of like there are multiple ways to write the same answer, because, like, again, for vector spaces, things are not unique, like a basis is not unique, and things of that type, but it is not as bad as it seems. So usually, especially for the relatively small matrices, like there are not that many variations you could do. um what I was going to say about what I wanted to say about the Gram-Schmidt method is that yeah, like the way I explain it, right, is like you start with a basis. I think basis, you want you to, let's say, well, I'll do it, let's say you start with a basis of V, right, at which all the vectors may not be orthogonal, right, and so the Gram-Schmidt process will make them orthogonal for you. So Gram-Schmidt will produce an orthogonal basis for you. Let's call it V1, V2, up to Vn. The thing I didn't emphasize is because, like, you know, in practice, when I'm, you know, if you notice, like, the problems in this Gram-Schmidt method, I have been giving you like the vectors of the basis in a specific order. The reason why I'm doing that is that actually the method does depend on how you order the vectors of the basis. So let me just show you what I mean by that. So the vector, so the vectors that you get do depend on how you order on which you call the first basis vector, the second basis vector, and so on. That doesn't, like, again, matter too much in practice, but do depend, because you only care about finding an orthogonal basis. So you don't care that there are variations, but still on how, on which on how you order the basis. So how you order the basis. So let me just do it in a concrete example so that you see that. So for example, let's imagine that, like, like the first vector I had given you is 1, 1, 1, 0, and the second vector I gave you was 0, 1, 1, 1. Okay, so those, I mean, it's very, like, let's say that's the basis of a vector space. Okay, this is a basis of some vector space. So what I'm saying is that here it kind of it's important that that like when I'm going to do Gram-Schmidt, it will, like, the answer that I get does depend on the fact that this was called the first vector and this one the second vector of the basis. So why does that happen? So what is an orthogonal basis here? Well, like, well, the way I taught it is like, well, you put them first as row vectors, 1, 1, 0, 1, 1, 1, 0, 0, 1, 1, 1. Okay, and then let's do a transpose. It's not too bad. It's just going to be 2 by 2. So this gives you 3. Actually, 3. This is a nice matrix. I mean, the numbers are not too bad. And then this is 2 and 2. By the way, I don't know if you noticed, like in these matrices that you get when you do always a transpose, that's always symmetric. So like, usually when you complete it, you don't need to complete every single entry because like it being symmetric, it would be, the same when you reflect it across the diagonal, but it doesn't, like you can still do all the multiplications, but I'm just saying this is always symmetric. So it's kind of just useful to know, but it's not that we will do too much with that information. But anyway, so in the Gram-Schmidt method, like I put this like basis like this. And I wanted, like, say, I want to, the idea, well, this is easy because there's only 2 vectors, but the idea is to get to you want this to be, upper triangular. So it's almost ready, right? Like the only thing I have to do is take care of these 2. So that just requires a single operation. You can do, for example, minus 2/3 row 1 plus row 2 into row 2. And if you do that, oops, let me put it like this. 1, 1, 1, 0, right? So if you do that, this one becomes 0, and then this one becomes 3 minus. I mean, it doesn't matter what it ends up giving, what number you end up getting here. So it's just minus 2/3. Minus Okay. So let's see if this. It's always good to check that you have the right numbers. And yeah, so what I'm saying is we're done because this is already upper triangular. And so the basis vectors are v1 1 1 1 0 and v2, which would be minus 2/3 1/3 1/3 1. Those are the orthogonal. This is the orthogonal basis in this case. Can we put the orthogonal basis? Okay, yes, correct. When you, like, for example, like if I multiply all of this by 3 and this by 5, they will still be an orthogonal basis. The convention, that's like a good question. Like the convention, I mean, the method is set up. If you notice what happened here, this first vector that you found, right, is indistinguishable from the first vector you got here, right? So actually the method is designed so that the first basis vector coincides. So just as a remark, it's like a useful remark or useful thing to know. This method is designed, the Gram-Schmidt method is designed so that kind of like you don't modify the first vector in your list. So it's not that it is true that you could like just multiply them by numbers, rescale them and still get something orthogonal, but it kind of in the process, like that wouldn't make that much sense because you do want to like like it is set up so that it just matches like the first vector that you had. So it's set up. Yeah, that's like right. I mean, yes, like you may have noticed it from the examples, but just I figure maybe right, it may not have been so obvious. So that's why I'm clarifying right now that does happen all the time. So that the first basis vector is the first basis vector is the same both in the non-orthogonal version and the orthogonal basis. So that the first basis vector of the non-orthogonal basis is the same basis vector of the orthogonal basis. So because of that, well, no, it's just it depends. Like it's okay. It depends. It's not that you're not allowed. If you only wanted to, it's just like terms of terminology, right? So if you are allowed, like how should I say it? Like if you wanted to, if you are only interested on finding an orthogonal basis, yes, like for example, you could find these two vectors and rescale them, right? And that's fine, that's allowed as an orthogonal basis. And what I'm saying is that if you find it like under the umbrella of what's called the Gram-Schmidt method, the point of the Gram-Schmidt method is that it's kind of like it just like the thing is like if you notice with this linear algebra processes, there are many multiple ways to to kind of come up with an answer. So like the point of an algorithm is kind of to this is like kind of like an algorithm. So the point of an algorithm is kind of to reduce the amount of freedom that you have so that you can get like so that like more and more people can agree on what the answer should be, right? So it's not that you're not allowed, it's just that like imagine it is easier to just program, like think about it like in terms of a computer, right? It's easier to write like a code for a Gram-Schmidt method where there are fewer choices to make than a code where you tell the computer, well, if you want to also rescale them, like you know what I'm trying to say, like it's just we're just trying to reduce the amount of freedom so that because otherwise like the answers like if you're allowed to rescale, the vectors, then yeah, we will all disagree on how our basis vectors look like. But actually, if you kind of do it with this algorithm, like like the freedoms that you had originally just like get reduced, so everyone would come up like to the same answers. If that makes sense. Is that making sense? So it's more like yeah. So right. In a sense, like the goal is that like everything must be like this. Like the problem in this course, all our matrices are like 2 by 2, 3 by 3, or four tops. Like I have given you like some with have like 3 or 4 columns, right? But you must think that this is designed, and the end linear algebra is designed like it is like what the thing that gets used in data science, where the data are matrices with hundreds of thousands of entries, so or millions of entries actually. So imagine just like all these like like machine learning programs like ChatGPT and all these things, like they work with linear algebra. So and they must go through millions of entries, like or data points. So imagine like just adding freedom to those methods. You want to minimize freedom as much as possible because that way it is easier to program and it is easier, to just like if you wanted to check there's a bug in the system, it is easier to do that if you can actually, if there's like it's a more clear path on what it's supposed to do, if that makes sense. So it's not that in a theoretical sense you cannot do it. It's just that like the point of the that's why it's called like an algorithm, or that's why I gave the name of to people. Well, those are the ones who, I guess, who came up with it. But that's why it's called Gram-Schmidt process, because it's just one way to do it. It's not making a claim that this is the only way in town to do it, but it's just that we want some sort of like uniform standards, because otherwise everything becomes a mess. So the Gram-Schmidt process, it is designed so that the first basis vector gets do not change, because it's like just like a useful convention. Because imagine like in a program, that means that in your first computer program you have a fewer operation to do, because the first step would just be copy the first basis vector. You know what I mean? If you wanted to do something to the first basis vector, then there's an extra operation that you are giving to your computer to do, right? Because maybe you want to multiply it by 3 or 4, and when you have to do this millions of times, doing an extra operation takes energy and money, right? And you don't want to spend money, extra money. So like in fact, like there are like all these like there's a lot of energy involved in algorithms, in how to try to do the algorithms in fewer number of steps. Because like again, like when the matrices are size 3 or 4, that doesn't make much of a difference. But then when the matrices have 10 million entries, it does make a difference whether like a small a small difference in that, it will it would matter a lot. You see, so it's more just to avoid a lot of options, basically, so that we can kind of all come to better of an agreement. So yeah, so like in the point, so in the Grand Schmidt, like when I was doing it, it kind of was implicit, but I didn't say it out loud. The process is designed so that you don't do anything to the first basis vector, because it saves you time. So in an idea, like the point of the Gram-Schmidt process is to try to get to an orthogonal basis in the fewer steps possible. So if you try to modify the first basis vector, that's just adding an extra unnecessary step. And then just to compare this, like what if we had chosen the opposite order for the basis? So what if we had used the basis in a different order? If we had reversed the order of the basis of the original basis. So imagine I get, it's going to be these exact two same vectors, but I'm going to change their order. So I'm going to call this one the first basis vector and this one the second basis vector. So it would, let's call it W1 and W2 to not make it like, you know, very confusing. But again, like I'm literally just changing the order in which the basis vectors appear. So now that's the thing, like if you look in terms of the matrix you're working with is this one now. Like in this case, the numbers were relatively easy, so I think A transpose will be the same matrix, but that's more of a coincidence based because of the numbers that I gave. Here, let's see. But even if this one is a nice example, because even if this matrix is the same, you'll see that the result is not the same. Yeah, it is the same. But now what do you have to do? You have to do this matrix with the matrix A. And so this is again, like just you want to get this to upper triangular. So it's just about putting a 0 here. You can even do the same operation as before, which is well, a similar operation is minus 2/3 here of root 1 plus root 2, right? That should work. And what are you going to get? You're going to get 3, 2. The important thing is that there's a 0 here. I don't care about anything else, so you can put like 3 minus 4 thirds. Like this is fine. I don't care about that. 0, 1, 1, 1. And then what do you get here? You get you're doing minus 2/3. So you put 1/3 here, 1/3. Sorry, yes. Oh, oops. So this is 1 minus 1 minus 2/3. Yes, that's 1/3. Good. And then the other one is 1 minus 1/3. That's 1/3. And the other one is minus 1/3. Let me, oh, minus 2/3, sorry. The last one is minus 2/3 because there was a 0 in this entry. Okay, so right, so in this case, the basis is 0, 1, 1, 1, and 1, 1/3, 1/3 minus 2/3. Yeah, it's almost impossible to avoid fractions, even if you start with it's almost impossible to avoid fractions, even if all the entries are kind of like the original entries are kind of nice. So they wouldn't, like, I won't give you like big numbers or anything like that, but yeah, like it's just basically there's no way to get, like, more or less there's almost no way to get rid of the fractions. And so compare this with the other one we had found, compared with the other one, like the original one that we had found, which was 1110 and minus 2/3, 1/3, 1/3, 1. So you see, I mean, they are if you compare the new one versus the older one, they are different bases. That's okay, because the point is that on a vector space, there are multiple bases you can find. In fact, even on a vector space, there are multiple orthogonal bases you can find. So there's nothing to worry about here. It's just that it, like, the answer does depend, like for this algorithm, the answer does depend on which one you decide to call the first basis vector, the second basis vector, and so on. And that's fine, but it's just that's why, like, in these problems, if you notice, like, the way I asked them in part was like by giving you already like an order for the bases, because otherwise, like, everyone could just order them in different ways, and that's just a mess. So it's just better to kind of standardize things by me giving you, like, oh, this is the first basis vector, this is a second basis vector, and this is a third basis vector, and so on. But like the nice thing, in a sense of doing it, I mean, the cool thing about the Gram-Schmidt process is that it yeah, it kind of you know it kind of leaves the first vector untouched, and and the idea is to get to to the upper triangular matrix on this side in the fastest way possible. So the point of the Gram-Schmidt method is kind of to if I had like another vector, like, imagine that I got this let's say this had been like, just to make it just to see if I can explain what I'm saying. Like, imagine I did this the same, but now with three vectors. Oops. Otherwise, this will not be clear. Just give me a second to see if this one works. I think this one will work, but I just want to double check it before I do something crazy. Um, 1, 1, 1, 0, 0, 1, 1. Yes, I think this one will be okay. Yeah. Okay, yeah. So let's say, I mean, I just want to, it's easier to clarify this, emphasize this with an example. So I'm just writing the same original vectors from before. I'm just adding a third one, right? So what would be the orthogonal basis here? I mean, the method is kind of smart in the sense that, I'm adding, like, an extra vector. So kind of you want to rely on what you did first. Like, so in a sense, like the new orthogonal basis should be like the older orthogonal vectors we found plus a new one. So it's not kind of like, it's not that this new basis will be completely unrelated to the previous one. It's actually kind of like consistent with the previous example. So if you add more new vectors, like kind of the basis will preserve the vectors from before. Otherwise, it's just like so silly because you would have to start again from scratch. So it's like what I'm trying to say is that this, since the first two vectors are the same, these method are the same. The idea is that the first two orthogonal vectors of the new basis will be the same as before. The first as the ones we found before. So it's kind of like almost where is it's kind of like almost opening, like, you know, this kind of was hidden from plain sight. So you kind of just work with these two at the beginning, and then you notice, oh, there was a third vector left. You don't want the method to kind of force you to start from zero again. That would be so silly, you know what I mean? So the method is designed so that once you do first vector is great, it's easy. You don't do anything. Once you do second vector, if they're further vectors, you don't want to keep going back and modifying them. So kind of the method is supposed to be in place so that everything that you did before kind of remains in place, even if you have further vectors. So just to show you what I mean, the matrix is now 1 1 1 0 0 1 1 1 1 0 0 1. And if you do A transpose in this case, what do you get? 1 1 1 0 0 1 1 1 1 0 0. So this gives you 3 2, and then this is 1, and then this is 2 3, and the other one is just 1, and this one is just going to be 2, and then this you get 2 1. Oh, let's see, this should be a, oops, this should be, this just be 1, and then right, let's see, this would be 2 2. 1 and 1. Okay, so what I'm saying is, like, if for example you look at these matrix, the first 4 entries here, right? The first 4 entries are exactly the first, like the entries of these earlier matrices, right? It doesn't. I mean, both were the same in this problem. So maybe I should just mark this one. But what I'm saying is that uh, so like the vector, when you added a new vector in the basis, it just adds like extra rows and columns to the older matrix that you were finding. So that means that you can rely on the results that you had from before. Otherwise, like, you know, the method would always require you to start from scratch every single time. That makes no sense. So and yeah, this is 1 1 1 0 0 1 1 1 0 0. And again, you can just do like -2, like what did we do in the first operation here? -2/3 or 1 row plus row 2. The thing is that now you could also, I mean, that would take care of the 0, but again, you want to get to upper triangular. So you do want like a 0 here. So you can also do, it's just a note to get a 0 there, you only need minus 1/3 row 1 plus row 3. Okay. So this is 3 minus 4/3. 3 minus 4/3 is 9, 5/3. Should be 5/3. And then this one is 1 minus 1/3. And then this one is 0. 1 minus 2/3 is 1/3. And then 2 minus 1/3. Oops, sorry. Yeah. 2 minus 1/3 is 5/3. Okay, so again, my point is that if you look at these first two rows, right, these first two rows are exactly the same that we had found at the beginning of our example. So these first two rows agree, and that's good because that just means that that just means that you should just modify whatever else is needed, but you don't want to go back and change those two rows again because like that kind of it's kind of screwing up what you already did. So it's just like the idea is to leave that as it is, and it's just like the only thing that you need to do now is just put a 0 there and then you're done. So it's not trying to it's not like the idea of this process is not to try to change the numbers here, because if you change the numbers somewhere in here, you're changing also these basis vectors, but they were kind of already the ones from earlier. So it's like the consistency is just to try to leave alone whatever you did before. Otherwise, so these two rows are the same as before. Same two rows. So the idea is not to modify them. So don't try to modify. Again, why would you do that? It just adds more steps and more time you're wasting. And here is kind of like a minimization of the amount of time needed. And so like the only step, the only thing that you have to do here to get a 0, if I'm not mistaken, is just to put like a minus -5, oops, sorry, minus 1/5 of row 2 plus row 3. Yes. And so that would give us whatever I mean, these will become whatever it is, like 3, 2, 1, 0, 5/3, 1/3, 0, 0, and I mean what 5/3 minus 1/15, whatever it is, I don't care. Because we don't have any further purposes for this matrix. So that's like whatever that it was, that's I'm fine with. So let's just put 1, 1, 0 minus 2/3, 1/3, 1/3, 1. And then, again, this is a little bit of, this is a little bit annoying. So it's, just to put it like here, it would be like 2/3 plus 215/15, and then minus 1/3. It's better in this one because there are so many fractions. It's better to write it all like I recommend in this case just to have like a step where you write everything down explicitly, because this is so easy to just get it confused in your head. So these will be what? 10 plus 12 over 15. And this one should be what? Minus 6 over 15. And this one should be minus 6 over 15. And this one should be 4 over 15. So the basis, like the basis is now V1, which was 1, 1, 1, 0. V2, which is minus 2/3, 1/3. One-third, one, and the last one, the V3, would be this mess that I just found, 12 over 15 minus 6 over 15 minus 6 over 15, and this is 4/5. Well, I guess here you can simplify, you can, if you want to simplify this, you could a little bit. I mean, I'm not too worried about, you don't have to do that if you don't want to, but this is like, yeah, like this is 4/5 minus 2/5 minus 2/5. Yeah, it looks a little bit better. But my point here is like, if you look at the consistency, it was like when you added a third basis, a third vector to the basis, like the new orthogonal basis is just the older one, right? This is the older basis plus a new vector. And so that's good. So this is old basis, old orthogonal basis plus a new orthogonal vector plus new vector. So what I'm saying is that if for some reason, like, someone decided to add 5 more vectors to the basis, like, you realize, oh, you're working with a vector space that is larger and has more basis vectors. What we know is that these 3 are ready to go, because like the method works in such a way that it kind of builds up on what you did previously. So it's not trying to destroy the previous vectors. Again, you kind of don't see that if you just start, or if you only start with the 3 vectors at once, you may not see that, but it's useful if you start first with 2 vectors and then you kind of focus on the first do it for the first 2 vectors of the basis, and then realize that there was this third one already there, and then you do see it kind of builds on the same stuff. Is that making sense? So just when you're when you are reducing the matrix, it's basically putting these zeros, like the most I'll give you is like 3 basis vectors, because otherwise this would take forever. So this is kind of like the top number of vectors that you would give. I'll give you like 3 for a basis with Gram-Schmidt, but it's just like literally just put a 0, like put these 3 zeros as fast as you can, and that's it. Like, and that's like, don't try to do anything else, and that's like how the Gram-Schmidt is supposed to work. But it's like it's an interesting method. But yeah, I figure I should make that remark, because otherwise, like, it could be confusing. Is that okay? Are there any other questions? I mean, it's kind of like, in a sense, well, if the thing is, like, if you look at the old exam topics, like the first exam was mostly about solving systems of equations. That definitely will just continue being here. And then in the second midterm, we had determinants, which we're using to find the eigenvalues and eigenvectors. So it's kind of incorporated there. And the vector space stuff, like finding bases and things like that, but we're also using that. So I'm trying to say that there's not that much from the first 2 midterms that is not being used already in the new stuff. So that's why I was saying that, most of the problems are kind of new. It's just that the techniques, there's not that many techniques that we have learned, so it is kind of like, oh, there's no, like, I cannot tell you just like, don't study determinants, because then you cannot do like the eigenvalues, eigenvector stuff, or like don't solve systems of equations, because then you cannot like find null spaces. So there's not much that there's really no topic like that in principle, it's just that like the problems, if the older stuff appears in the new stuff, it more likely will appear. I mean, like the older topics, if they appear, they will more likely appear somewhere being used in the new stuff. But you should still, like, what I would say is like, just check that, take a look at the old exam problems and like the practice problems for the midterms. Um, but yeah, everything is kind of like, all the topics from the previous exams are covered, but just in a slightly different way, if you know what I mean. Uh, but you could still have, I mean, you can still see like a problem from like, is this a vector space or things like that. So like, just go over like I mean, just my recommendation would be like, look at the practice exams for the final and the the first two midterms, and look at the exams also as well. And yeah, but it's not, the thing about that, this is kind of weird about this course, like it's just really a lot of like, it's very, the material, it is very repetitive in a way, because if you really think about all the problems, like more than 50% of the problems more like involve like reducing matrices in some way or in another. So you kind of have to just, that's just more or less the only thing we learned, except for computing determinants. I think that's a slightly different thing, but yeah, you should just you should definitely review everything. By like, you can look at I think on one of the announcements I had posted like, some practice exams from the last semester and things like that. So but I mean, there will be definitely finding a problem about the exponential of a matrix, that will be there. Finding Gram-Schmidt, that will be there. Then like finding like, what else have we done here in the new stuff? Finding a projection matrix, that will be there. So there will be a question for every single new topic that we have done. That's already like 6 problems, I think, if you just go over, like if you just check like the practice exams and things like that. 6 or 7 problems. And then yeah, like there will be like, the remaining ones may look kind of more like from older stuff, but at least, if you look at the practice exams, like you can see like, it's easy to identify right. It's more, it is like, think about it almost like as a third midterm plus some crumbs of older stuff. But yeah, I would definitely ask a question for at least each of the new topics we did. So like we did the conic section yesterday, there will be a conic section problem. The Gram-Schmidt, definitely there will be a problem about that. Finding the basis for the orthogonal complement, there will be a problem of that. So like that's very like, if you look at the practice exams, you can identify the new problems, and though there will be one of each for each of these new types of problems. And then yeah, something that would be look more like older stuff. But the thing is, like the new stuff already includes a lot of the older stuff, so that's why it's kind of hard to to break it down. Yeah. Anyone else? Well, let me do another example of this projection stuff because we didn't get a chance to do that many in class. So let's just find another projection matrix. Let's see. So the idea again, like the idea of the projection matrix is hard to make a picture here, but you have like you should think about this as being like some sort of shadow. So you have like a vector space W. And you have a vector which you can call V if you want. Okay, so the projection matrix is the projection of V onto W is going to be this shadow, this green shadow that you see here. So let me, I think this colors, like I'll color it differently. So the projection of, yeah, so the projection of V is going to be the shadow that you see here on the picture. The important thing is like the formula. The formula is you know, it's always the same. It's just this is V dot W1 times W1 plus V, let me write it down. V dot W2 times W2 dot V dot WK times WK. We're here W1, W2 up to WK are on orthonormal basis of W. So let's just try to do this in an example. Let's say, for example, the W is the vectors X, Y, Z, W, where so again, what this means is that the condition for a vector to be in this vector space is that the first entry is half the second entry, and the third entry is 2 times the fourth entry, right? So usually for these problems, like the basis, I mean, when I write down the W's, the vector space, it should be very easy to find the basis. So the basis, like, I mean, it's just like if you start like with X, Y, Z, W, you can replace X as Y over 2, Y. And then Z is 2W, and then W is W. And so, you know, this is Y, 1/2, 1, 0, 0, plus W, 0, 0, 2, 1. So this is the first basis vector, W1, and this is the second basis vector. Okay, let me, I, um, this is I mean, those are the basis vectors. It's just notice that they're already orthogonal. Their dot product is already 0, so already orthogonal. So the only thing that we need here is to in this formula, we do need the vectors to have length 1. So let's see what are so we have to, the w's that we care is just 1/2 1 0 0 divided by its length. So what is the length of this vector is like, remember the Pythagoras theorem, you square each entry, so it's 1/4 plus 1 plus 0 plus 0. So the first basis vector is really, this is, what? Oh my God, this is going to give 5/4, so it's √5/2. And this is the same as 1/√5, 2/√5, 0 0. Okay. So that is the first basis vector. Because that one has length 1. I mean, the important thing in this projection matrix is that the length for it to be 1. So that one is okay now. And then W2 is 0 0 2 1 divided by its length, which is 0 plus 0 plus 4 plus 1. Okay, so that's the new basis vectors. So there are just the older original ones, but you're rescaling them so that their length is 1. Okay. So those are not that bad. It's also kind of similar to the previous problem. It's more or less unavoidable to not have fractions somewhere because there are so many rescalings that you're doing. And then the projection matrix is well, it is V dot W1 times W1 plus V dot W2 times W2. Okay, but what is V? I mean, I don't know what V is, so you just call it X, Y, Z, W. Like I can, in this picture, you can think of V as X, Y, Z, W. So who knows what that is? W1, we have it already here. So it's 1/√5, 2/√5, 0 0. And that, whatever that dot product gives you, gets multiplied by 1/√5. Okay, so that's the first, like all of these is this stuff, and then the others, the second summand is the same but with W2. So it is a dot product between X, Y, Z, W and W2, but W2 is okay. Maybe just let me change colors. So this corresponds to this stuff, and this thing corresponds to this stuff. Okay, so that's what each summand is. It looks intimidating, but the dot products are not that bad. So it's just x plus 2y/√5. That's what the first dot product gives you. 1/√5, 2/√5, 0 0. And then the other term is what? The other one is 2z plus w/√5 times Okay, and that's like the root of 5. There's a root of 5. I mean, this is a number you can put in every entry, so you get x plus 2y over 5. Then you get 2x plus 4y over 5, 0, 0. That's what the first two entries give you. And then you get 0, 0 for z plus 2w over, oops, plus 2w over 5. And then 2z plus w over 5. And finally, you combine, so that means that the projection onto w of v is like, what's this vector? Is like you just add them together, the two vectors. This is easy to add. And like the projection, let's see, those one. Oh, well, you have to be careful here. Oh, so sorry. I'm so sorry. These I write terrible numbers. This is a 2, right? It cannot be because all these equations are linear, so you cannot have like x equals y over 2w because oh, okay, let's see what you're saying. X equals y, does that right, like that x equals y over 2w, you cannot get it from these two because like the x, y are in their same equation, and the c and w are in the same equation. Yeah, I think how I wrote it earlier may have looked like a z, but definitely like, the equations have to be linear. So I couldn't have had like one of the variables in the denominator, if that makes sense. Or I don't know what, yeah, it may have this. No, you're fine. I should write it more carefully. But yeah, like that's the other good thing about linear algebra, that like, usually the equations, like when the variables appear, like they just like, they shouldn't appear like in the denominators or things like that, because it wouldn't be linear equations. And then from there, you can extract the projection matrix. Is literally the coefficients. Like that is something we had done before. Like this is, for example, the typical problem that we did for the first midterm. Find like the matrix that would take a vector into something like this. So it's just, you just copy the coefficients. It's 1/5, 2/5, then 0, 0, then 2/5, 4/5, 0, 0, and then the other one, it looks like 0, 0, 4/5, 2/5, and then 0, 0, 2/5, 1/5. So what this means is that but it's better to like maybe think about it in this formula. What this formula says is that I want, like, the idea of this matrix is to force the vector v to be in this or vector space, right? So to force it to be inside this vector space, its first entry should be 1/2 of the second entry. So if you look at this one, the first entry is 1/2 of the second entry, and the other condition was that the third entry had to be twice the fourth entry. And if you look at this entry is twice this one. So it, like, the matrix is kind of trying to force you to satisfy the equations of the vector space in the most in the nicest way possible. So the way it decided to do that is just like, to like, it's kind of like it kind of like tries to average these two numbers, x and y, but has to weight them differently because you want one of the entries to be half the other and things like that. But the matrix is really trying to put you in the vector space as in the most like subtle way possible. So, and the cool thing about this matrix is like you can check. I mean, it's actually a little bit tedious, but it will square to itself, which again is that thing that I said yesterday, the shadow of the shadow is just the shadow, right? Because once you are inside, you don't have to do anything else to be inside. So the matrix will not try to modify you anymore. So that's what's the fact that the square of the matrix is the same. And the other thing that happens in these cases is that I mean, they will always be symmetric as well. If you notice here, I mean that it's not that you have to, you know, this one is not like a practical one to check in practice. Like you don't want to square this to just realize that it's the same. But this one in practice can be useful to check that you have the right entries, right? Because you know, if this doesn't look symmetric, then it could not have been the projection matrix. So um so yeah, but it is these projection matrices are kind of fun because of that. Um, if you want. I mean, it's like a tedious calculation. So it's a bit tedious. But right, that's how in practice you find the projection matrix. Is that okay? Are there any other questions? Let's see. Oh
Professor,
yeah,
could,
that one.
yeah,
That one
could
is
you explain a little bit for that? Yeah, thank you.
yeah, sure. Yeah, that one is fun. So if like it's just saying that A and A transpose have the same eigenvalues, basically. So show A and A transpose have the same eigenvalues. So what are the eigenvalues for A? Remember that the eigenvalues for A can be found by solving determinant of A minus lambda identity equals 0, right? Those are the eigenvalues for A, right? What would be the eigenvalue equation for A transpose? That the determinant of A transpose minus lambda I equals 0. Is that making sense? But if you remember, the determinant of what's the cool thing about the determinant? The determinant of a matrix is the same as that of its transpose, right? So this is the same as the determinant of A minus lambda I transpose. Is that okay? Because the determinant doesn't change. You know, the determinant doesn't change when you transpose it. But then what is the transpose of like a sum or like a subtraction of two matrices? It's just like the individual transposes. So this is like the determinant of A transpose minus lambda I transpose. So kind of like the transpose, like, you know, it makes sense because the transpose is just changing rows with columns, right? So if you have like a sum of matrices and you transpose them, that's kind of like changing each of individually into their permuting the rows and columns in each of them individually and then combining them. So this is just that. But A transpose is A transpose. I don't know what that is. Lambda is just a number, but what is I transpose? Like, what's the transpose of the identity? The identity is itself its own transpose, right? So you see, like that. Actually, these two equations, right? These two equations are really the same equation, so that's why the eigenvalues are the same. Is that making sense?
Yeah, thank you.
Yes, no problem. Yeah, so it's just yeah, it's just useful to right, like the so what I used here is that I used that A plus B transpose is A transpose plus B transpose. So So yeah, if you transpose the sum, transposing a sum is the same as transposing each individual matrix, which might make sense. And the other two useful properties about the transpose, I mean, the transpose of a transpose is a matrix itself. That kind of makes sense, because it's kind of like you turn the rows into columns, but then you're turning them into rows again. So you should just end up with the same stuff. And the other one, which is actually okay, this is this is not sure if I've written it before. We haven't really had a use for it, but when you transpose a product, that is a product of the transposes, but in the opposite order. So I mean, yeah, there's no it's just useful to know. It's not a property that any of our problems require that we have done, but it's just useful to know that it's around. It is analogous to the inverse property, which I think is I did write some time ago, that AV inverse, well, if the matrices are invariable, or is V inverse A inverse when AV are invariable. So for transposes and inverses, there's a formula for the multiplication, but it's just it's not just taking their individual transpose or individual inverses. You have to switch the order of in which they appear. So that's the only thing that you have to remember for those.
And I have a question for the formula A equal to Q times D times Q negative 1 power.
Right.
Q negative 1 power always is the symmetry with the Q.
Yeah, you mean in this
Yeah.
in this one, what were you asking me about Q to the negative 1?
Yeah, that's always that is always symmetry with the Q.
It is Q inverse. I mean, this refers to Q inverse, right?
Yeah.
But now you're saying if that's the same as what?
Symmetry. I mean, the Q negative 1, whether is the symmetry with the Q. Like in the homework, let's see which one is. In the homework 3, for the question 2.
Okay, let me check. That may be easier. Right. Let's see.
I just don't know how to get the question, the Q negative 1 power in that. Because I use the formula, which is Q negative 1 power equal to 1 over
right. Yeah, you can use
symmetry and time that, but that I got a different number that what you show. So
yeah.
But if that is the symmetry with the Q, that would be just showed up directly. So
So the inverse for a matrix, right, is 1 over the determinant of A in the 2 by 2 case, right? It is dA. Is it like this?
Yes.
And so what is in this case, if you have the matrix 1A01, right? It's like the determinant is 1, right? So it's 1 over 1. And then the formula says the fourth entry goes to the first entry, and the first entry goes to the fourth entry. So that's just 1 and 1, right? But then the formula says that this entry is just minus the second entry. So it's minus A, and this entry is minus the third entry. So it's 0. It's just that it's not, the A has a different meaning here, right? Because here the A is the first entry, but here A is the second entry. Like, I think it's, it would be maybe less confusing if you think of this as B, right?
Mm-hmm.
So it would, if that would be the formula, right?
Yeah, yeah.
But it's just that I'm calling this entry not B, I'm calling it A. So, but it's just better to think about in terms of like what the formula is saying. What the formula is saying is that the diagonal elements get switched. So the fourth entry goes to the first one, and the first one to the end, the last one, and then the off diagonal entries get multiplied by -1. And if you remember it that way, then yeah, it's less confusing. But is that making sense?
Yes, but why for the determinant A is equal to 1?
Well, the determinant is just you know, the product of the diagonal, which is 1 times 1, and then this one gives you 0.
Yeah,
The
yeah.
other, I mean, actually, like this one is relatively fast, that you can just do the identity method if you want. So to find the inverse of a matrix, remember, you can also you know, put the identity to, and try to reduce this to the identity here. How can you reduce this to the identity? You just have to do minus A row 2 plus row 1, and then if you do that, you get like the identity here, and then you get 0 minus A 0 1, and that has to be the inverse. So in this case, it was not too long, because it was already upper triangular and at 2 by 2. So like doing the identity wasn't it doesn't take that much time. But yeah, so either if you use the formula for the inverse, you just have to check, like, think of the formula in terms of what it says, not like the specific names for the variables, because that could change from time to time. Right?
Gotcha. Thank you.
Any other questions? Let's see. So the other one, oh, yeah, I don't know if you had seen this one as well, which is also similar to one of the earlier problems that I just did. Like if lambda is non-zero and it's an eigenvalue value of A, or sorry, let me put it like this. If A has an inverse, if A is invertible, and lambda is an eigenvalue of A, then 1 over lambda is an eigenvalue of A inverse. I don't know if you saw that one, but it's a fun one as well. The idea is that here's the thing, like the thing that is interesting in this one is that, again, the eigenvalue for equation for A is this one. This is like the equation for eigenvalues of A. But the eigenvalue equation for the inverse would be A inverse minus lambda I. The problem is that this cannot be solved as the previous question with the transpose. The issue here is that you know, the transpose, like the inverse is not at all the inverse of a sum, assuming that exists, is definitely not the same as the sum of the inverses, even if all the matrices it's not the same. Even if every single matrix had an inverse, like the inverse is not additive in that way. Very unlikely. So you cannot just like kind of like, you know, apply like the inverse in both sides or something like do something like that. It's actually more convenient here to just start with the equation for eigenvalue and eigenvector. So what does it mean to say that lambda is an eigenvalue of A? That just means that A V equals lambda V, right? And then what you have to do is just multiply by A inverse on both sides of the equation. So what happens here is that this is already the identity, so you don't have to keep writing it. That's fine. And what happens here is that lambda, you know, it's like you can take it out of the multiplication because it's just like a constant. So that tells you that you know, so that says that 1 over lambda times V equals AV, A inverse times V. But that is precisely saying that V, I mean, you can write it in the opposite order so that if you prefer to write the matrix, see the matrix appear like appear on the left-hand side. So that is saying that the matrix A inverse times this vector is 1 over lambda, the matrix, the vector V. So that's precisely like the eigenvalue equation, but for lambda inverse, right? So this is like lambda inverse times V. So that's just saying that lambda inverse is an eigenvalue of A inverse. So it's kind of like an example where it was a lot more useful to just start with the original definition of an eigenvalue than trying to find the eigenvalues from the determinant equation. Yeah, let's do one. Let's see. Which one should I do? One. I just don't want anything with weird numbers. Okay, let's do something like this. Let's see what happens if I do this. So in the conic problems, again, in all these problems, it's like the matrix is just the coefficients. So what is multiplying x squared is 4. So that's goes in the first entry. Then in the fourth entry, you have to put what's multiplying y squared. There's no y squared here, so you should put a 0. And then outside the diagonal, you have to just put the number here, but divided by 2, so it's 1/2, 1/2. Okay. So now what are once you so the matrix can always be read from the coefficients of the conic equation. It always has to be symmetric, so that's a good thing that you should notice. So that's why to make it symmetric, that's why we have to kind of split this one in half. So to kind of like share it among these two entries. That's the idea. Now, what are the eigenvalues of A? Let's see. I hope it's not something too nasty, because I'm just coming up with it right now. So that has to be equal to 0. So it's better to just write it as 4 lambda squared minus 16 lambda minus 1 equals 0. Okay, let's see. This is going to be a little bit ugly in terms of the numbers. Let's see if I can just change it a little bit to not have something that's nasty. So, like the easiest fix I can make is just put like a 2 here. I just don't want the eigenvalues to look too ugly. So that we don't have to work with very crazy square roots. So I'm just changing, I just multiply this by 2, so this just gets divided. And now this looks a lot easier because, it's a lot better because, yeah, just better to have like a 1 here. That's lambda squared minus 4 lambda minus 1 equals 0. Okay, so again, since I'm just coming up with these numbers, the easiest thing I think to find it won't be that bad, but yeah, you will need to find this with the formula for the quadratic. So it's minus b plus minus root of 16 minus plus 4 over 2. So the first eigenvalue will just be okay, and this is, let me just put it like this. This is going to give you 20, which is 2 root of 5 over 2. So the first eigenvalue is going to be 2 plus root of 5. It's not that bad. And the second eigenvalue is 2 minus root of 5. Okay? So one eigenvalue is with a positive sign and the other eigenvalue is with a negative sign. So lambda equals 2 plus root of 5, or lambda equals 2 minus root of 5. Okay? And so let's just find the eigenvectors. The eigenvectors are, okay, what is the eigenvector? Oh, by the way, yeah. So this is already enough to say whether the conic section is a hyperbola or an ellipse, right? So what is this in this case? It's a hyperbola, good, because the eigenvalues are of different signs, right? So this is obviously positive. This one is positive, that's not a problem. Root of 5 is a little bit bigger than 2, right? Because root of 4 is 2 already. So this one had to be negative. So yeah, since the eigenvalues are opposite signs, they are, it is a hyperbola. So it's a hyperbola since eigenvalues are opposite signs. So that's the first part of the conic section problem. The second part is just to identify the matrix of rotation. Because the idea is like this hyperbola, I'll show you how it looks like on a GeoGebra in a second, but this hyperbola kind of will look like a little bit tilted. So to find like how much you kind of have to rotate your face to see like the hyperbola in the standard way, you kind of have to find the eigenvectors. That's what the eigenvectors are for. So let's do the eigenvector for lambda equals 2 plus root of 5. That is the null space of is 4, 1, 1, 0 minus 2 plus root of 5 1001, that gives you what? It's a little bit, it's not too bad actually. Okay, and then the easiest thing here to find this null space is to do like you know, to do something like two or let's see, you do like do -2 minus root of 5 row 1 plus row row 2 plus row 1, because there's already like there's already a 1 here, so just take advantage of that one. So if you do that, then this is 1. Okay, this will give you 0. And the thing is that this one will also give you 0. It's a little bit harder to see, but it will be, let's see, 1 minus, because this is -2 minus root of 5. And then there's like a minus here. So it's actually better to, like, I should have written this with a, this looks a lot better now. It's better to have left the minus sign upside of everything. Yeah, it looks better now. So if you do that, the thing is like, this will be like the difference of square formula. Right, because it will be 4 minus 5, so this will give you -1, and then 1. 1 with -1 will give you 0. That kind of always needs to happen more in these types of problems. Like one of the rows should become 0, 0, because there are two different eigenvalues. So there can only be at most one eigenvector for each eigenvalue. So it kind of had to be 0, but it's still good to check that it was correct so that you didn't make any mistakes. And so the equation, oops, I should still write it with minus. So the equation is just x minus 2 plus root of 5, y equals 0. And so, yeah, x is 2 plus 5, root of 5, y. So the eigenvector is just 1, 2, sorry, it's just 2 plus root of 5, comma 1. So that's one eigenvector. The only thing is that it's a little bit, you need to make it of length 1. So what is the length of this eigenvector? The length is the Pythagoras theorem, which is square each entry, and then add them together and take the square root of that. So it's like, 4 plus 4 root of 5 plus 5 plus 1. Something. Okay, again, like the numbers are a little bit ugly because like I'm doing it on the spot. I would like if I had chosen better, like if I had chosen better coefficients, like eigenvalues would be nicer, and so this wouldn't be as it wouldn't look as bad. But it's not. Yeah, it's okay. That can be done. So yeah, it's that you don't need to simplify it anymore. Like the only thing is that you can put this like this. So you just divide by its length. Okay, yeah, it's a little bit messy, but that's like the first eigenvector. And then the other one, for the other eigenvector is with 2 minus root of 5. For the eigenvalue 2 minus root of 5, what's the eigenvector? Well, what was the matrix? It's 4, 1, 1, 0 minus this. And again, it will be very similar, a very similar idea. So you want to do something like -2 plus root of 5, row 2 plus row 1 to put a 0 to make everything in the first one zeros. So it will be similar here. The eigenvectors actually end up looking to relatively similar because they are, there will be the columns of this rotation matrix. So, so that's the eigenvector, but you have to rescale it. So the length here is just the length is 2 minus root of 5 squared plus 1. And this is it's very similar. It's 4 minus 4 root of 5 plus 5 plus 1. So it is 10 minus 4 root of 5. And so the eigenvector that you really working with is that the one we found, but rescaled. So it's 2 minus root of 5 divided by root of 10 minus 4 root of 5. And then 1 over root of 10 minus 4 root of 5. Okay, so let's see. Let me check here. Am I doing this? Let me see. I think it's fine, but let me find the eigenvalues. Check that I have everything correct. Yeah, the eigenvalues are fine. And then this is fine also. Okay. So, yep. Okay. Yeah. So let's just put what we found here. So for lambda equals 2 minus root of 5, sorry, for lambda equals 2 plus root of 5, the eigenvalue was the eigenvector was this one that I found. And for lambda equals 2 minus root of 5, the eigenvector is this one that I just found, right? The thing, what looks a little bit odd in this case is that, yeah, that's what I'm going to try to fix. So again, like the numbers, like they won't be as, like I promise you, like you won't, like it's not going to be as messy as in here. But what you can do here, like the problem is that the problem is that the denominator here, this one has a plus and the other one has a minus. So what you can do is this trick if you wanted to compare them more properly. So yeah, you can do this trick called like rationalizing the expression. Let's see if I can do this. Okay. I'm just trying to make it like look better. Okay, okay. Okay, yeah, there must be, uh, right, that's, that's also, okay, yeah, okay. Like, the thing is, like, this is going to be, right, you want to compare these columns, compare this with, cosine of theta minus sine of theta, sine of theta, cosine of theta, right? So yeah, by comparison, you know, this, like, as you were saying, this, like, in this one, like, the both entries are in a sense like positive, and in this one is negative. This is fine because this one is definitely going to be negative, right? It's just that it's a little bit messy because of this thing with these stupid different fractions, but it's just you know, if you compare them, yeah, the rotation matrix should actually, this column should just match with this one, and this one should match with this one. It's just like, I mean, if you really want it, I mean, it will be fine because it's going to work, because that's how the theory is supposed to work. But what I'm saying is that like, in a sense, it should be the case that, right, like that mine, it should be true. It should be true that, you know, that if you multiply the second entry by -1, then you get the third entry. Yes, that will happen. It's just that, you know, it is a bit, because it has so many fractions, like, it's not so clear to see. You have to simplify the expression. But like, again, like, I won't give you problems where, like, you know, the numbers are so nasty. But to check that, you could, you know, you could rationalize it, but it's not, but you don't need to, but it will happen. Because I checked, like, yeah, it was like, just, I mean, because the numbers were ugly, so I checked it on Wolfram Alpha just to make sure that it was fine. But it is fine. I mean, these are okay. It's just, yeah, it's like a little bit ugly in terms of like but I did have the correct eigenvectors and everything. So in fact, like, in fact, you can even see, yeah, you can even see that their products should be, there's, at least it's easy to see that they are orthogonal. You know, they're perpendicular, because if you do the dot product of this with this, 4 minus, yeah, if you do the dot products, they are definitely perpendicular, and both have unit length. So it does have to, it will happen. It's just like not so clear in this example because of all these fractions. But these, right, as you were saying in the chat, all of this is like one with positive entry, so you can just identify it with this one, and this one you can identify with the second column. And so, like, if you want to go to GeoGebra, let's see if I can show you this on GeoGebra, how this looks like. If you go to GeoGebra, then the equation of the conic, oops, the equation of the conic was for, oops, 4x squared plus 2xy equals 10. Okay, so you see like there is a hyperbola and there's this tilt, and then for the tilt, what you can draw, I mean, you could enter like these vectors. I'll enter them without their rescaling because it would just take me forever to write it with their rescalings on GeoGebra. But like one vector was like 2 plus square root of 5 comma 1, and the other vector was 2 minus square root of 5 comma 1. Oops. So you see, like I'm entering the vectors without their rescalings. That's why they have a different lengths. But the important, like you can already see there that they're perpendicular, right? It's, you can see that they're perpendicular, and you can see that if you kind of rotate your, just imagine rotating your head, so that that kind of becomes a new X and Y axis. I mean, well, another way to rotate it is this way. Yeah, just imagine you rotate your head like this way, so that like your X axis, new X axis is like in the direction of this one that's called V. You'll see that the hyperbola like kind of looks like standard. But yeah, like it's just identifying the like you could it's like a different, slightly different, difficult angle to find here, obviously, because it has so many square roots and everything. But I'm just saying, like, there is a rotation angle that you could extract from here. Like, just to finish this up, let me. What is a rotation angle? The rotation angle is literally, arc cosine of 2 plus root of 5 over root of 10 plus 4 root of 5. Of course, no one like would know that without, and that is something that like you wouldn't, I wouldn't know how to simplify that, right? You would just leave the answer like that. But I'm just saying that there is an angle, and that's the one. Okay. But okay, I think this was good that we did this example. So yeah, just practice those problems, but it will be relatively, I think like the exam will be very, if you did all the practice problems and all of that, you'll be fine. Like it's not too, like it's very similar to those practice problems. So yeah, there's still office hours if you want. So well, just email me about that.
Professor, could you go up a little bit, go back to the
Here or
the previous question?
oh, the previous question.
Yeah, okay. Yeah, this one. Could you explain more like why the vectors equal to what is that called? Something else times a negative 1 power times the vectors.
Well, the thing is like that lambda being an eigenvalue just means this, right?
Yeah.
But I want an equation for A inverse, so I have to make A inverse appear. So that's why I multiply both sides of the equation by A inverse.
Mm-hmm.
But once you do that, these two cancel, right? And like a constant, you can take it out of a multiplication. So that's why you just get A inverse D.
But when you cancel that, that should be the.
Oh, there's an identity here if you want, if that's what
Oh yeah, because yeah.
But an identity is kind of like harmless, right? Because it's like a multiplication, so you don't have to write it anymore.
Yeah. True.
Is that making sense?
Okay, makes sense. Gotcha. Thank you.
Okay, good.
Could you back to the notes for a little bit so I can copy it?
Oh yeah, sure. I'll also upload them. But yeah, you can. Is it sharing? Do you mean this part?
Yep.
Professor, I sent an email to you about how I had a conflict for the final exam time.
Mhm.
and I didn't get a response back. So I was just wondering if
Oh, when did you send it?
on
uh,
Friday.
Oh, sorry. Let's see. Oops. Uh, just give me a second. Let me see if I find your email. Um, um, well, yeah, what I was telling people, yeah, I don't know why. If you want to reply to it again, I'll reply to you. But yeah, the only thing I was saying is that I still don't know how many people would end up taking the makeup. So like that's why it wouldn't happen this week. Most likely, I would just schedule it for Monday of next week. So it's just that I still don't know the time because it would depend on what works for everyone. If that makes sense.
Okay, so it wouldn't be tomorrow then?
The makeup would not be tomorrow for sure. Yes.
Okay.
And not even this week. It would be on there like until Monday.
Okay, thank you so much.
No.
Also, I had another question. On like the syllabus, it says like there's like a grade portion for like Canvas assignments. I
Oh
was
right. I think we didn't have any, so I'll just give everyone those points.
okay.
Yeah.
And also, I know the exam is supposed to be cumulative, but on the like practice final exams you gave us was mostly questions from like part 3 of the course. So will the final mostly be on
Oh,
part?
I said that was like only, I mean, yes, that's true. But also because I was just adding new problems because you kind of had like, older problems for the other stuff. So let me see, where do yeah, I know what you're talking about. Where did I add that practice you mean like the ones that say like exam final 14, exam final 9?
Yes.
Right. Those were the final exams that I actually used in the spring. So if you look at them, like the majority are new stuff. So that's kind of like a similar ratio to what I'll do here. So
Oh,
yeah. It's just that for this one, I'll do 10 problems. Like the ones that I did in that spring were just 8. But I mean, besides that, like, yeah, the overwhelming majority of the problems are kind of on the new stuff. It's just that a lot of the new stuff require older stuff methods,
so this will be 10 problems?
The exam will be 10, yes. 5 and
Okay.
5, basically. Each one.
Okay.
Yeah.
So if I'm gonna take the makeup, I just
would-
don't have to like worry about the test tomorrow,
Yeah,
right?
you shouldn't, yeah, don't, you're right.
Okay,
Don't
okay.
do anything to it, yeah.
Okay. Thank you so much.
Okay, bye.